Hi everyone, this lesson is for geometry students. We are beginning Dialations. This is chapter 3, day 1. So let's get started. So we're going to start off with a warm-up, and this is just ratios and right here. And we're going to try to simplify this ratio. And I would divide by 5 into both 15 and 25, leaving me 3 over 5. I would cancel one of my y's out here. That would be gone. And then I would have 2 left. One of my x's down here would cancel with one of those. And then on the top numerator, I would have 3x over. And on the denominator, I would have 5. This x canceled. And then I have y squared. And so that would be my simplified answer. For these problems here, these are not expressions, these are equations, so we're actually solving, not simplifying. So for these problems, if you have one term on the left and one term on the right, you can cross multiply, and so that's what I'm going to do. I'm going to multiply 2 times x. I'm going to get 2x equals 8 times 5, which is 40. I'm going to divide by 2. I get x equals 20, and I'm going to put my answer in solution sets because these are solutions to an equation. All right, next problem is, again, one term on the left, one term on the right. Yes, I can cancel. I can like divide this to make it smaller. If I did that, I'd divide by 2. Dividing by 2 here would give me 9 over 10 equals 9 over 2x. And sometimes even just doing that, you can very much visualize that x would need to be 5. However, I mean, yes, you can always cross multiply. 9 times 10 is 90, equals 9 times 2x, which is, what is that, 18x, and then divide by 18 and you get 5. For this problem, there's no dividing. You can't divide x and x. You can't divide 4 and 4 because these are actually quantities. And in order to cancel those, they would have to be the exact same quantity, which they're not. So we can't cancel those. So we're just going to cross multiply. We're going to go 5 times x plus 4 equals 6 times x minus 4. And I'm going to distribute. I get 5x plus 20 equals 6x minus 20. I'm going to move this 5x to the other side. So subtracting 5x gives me 1x left. I'm going to add 20 to both sides. I get x equals 40. Again, these are solution sets. These are solutions, so put your answers in solution sets. All right, so today our learning targets are basically to learn about dilations and some of their characteristics. You should be able to determine dilations having equal angles, proportional corresponding side lengths, and also we're going to talk about a little bit of similarity and being the transformation of an actual object. As you transform it, it becomes something different, and that's, you know, basically a transformation. You're going to see something like this on your homework, and I just want to bring some thoughts to your mind in that, you know, there are actually a small triangle here. I want to just point this out to you. This small triangle here, and then you've got this larger triangle here, okay? And so what's happening is that a lot of times we're going to remove this little triangle because what we are trying to do is we're trying to compare these two triangles that are similar and what makes them similar, you know, and finding, you know, their ratios and how they can be equal. So that's what our goal is today. So let's see how we do with that. Basically, a dilation is a transformation that enlarges a figure while maintaining the shape. We call that a dilation. And so in this case right here, like if I were to cut this guy off like this and then come back up and do this like this, what I would get again were these 2 triangles that you saw on that previous screen. What I would expect is that you realize that, yes, I'm going to have 2 little triangles. I'm going to have a larger one and I'm going to have a smaller one. And then by having these 2 triangles, I'm going to be comparing the sides. Like, let's say this is 5, and this side might be 10, right? So if I want to find, and I know this side over here is, let's say, 13, what would this side be here? And so in order to do that, I would make some sort of comparison, or, you know, make two ratios and put them together, and we call that a proportion. Okay. And so like I would say 5 is to 10 as 13 is to x. See, I'd go this side here is to this side as this side is to this side. And so I would do something like that. And then of course I would cross multiply. 5x equals whatever 10 times 13 is. And I'm not going to multiply that out because I'm going to divide out 5. And then by doing that, I get x equals 2 times 13, which is 26. So this value over here for this length would be 26. And they are similar, meaning, because one is dilated to another value, we've transformed it. So again, a dilation is a transformation that makes a shape of a figure but multiplies the dimensions by some sort of factor. And so a dilation in a shape is stretched proportionally. So, you know, we start off with a smaller shape, we have a large shape. That diagram below is basically saying ABC is dilated to form A prime, B prime, C prime. So basically this little triangle here was enlarged so much that now it's this value here. And that by doing that, we actually have something called a scale factor. And if we went back to that last slide where we were working here, if you notice, I can make a scale factor by comparing two sides, like 5 is to 10. Well, that's a half, right? So that means that this value here is a half of that. So we dilated it down to a half. And so actually that dilation is a reduction instead of an enlargement, right? Okay. All right, so notice that while a dilation changes the size and location of the original figure, it does not rotate it, it doesn't reflect it, it just transforms it to be a bigger or smaller value. The dilation, the enlargement encloses the original as shown. So basically what's happening here is we have an enlarged value. This scale factor, right, would be 5 to 15. And so for this value here, 5 to 15, that's 1/3. So that means that this little doggy here is 1/3 of that value. So if you take this value, you're enlarging it by 3, or you're reducing it by 1/3. So, okay. All right, so on a piece of paper, what we're going to do is we're going to actually create some sort of dilation. So what I want you to do is just sketch a scaling triangle. Remember, that's where all sides are different values. So just, it doesn't have to be perfect, just needs to be, you know, a sketch. And then the next thing I want you to do is I want you to label a point out here, and I want you to call it P. So you have your picture here, and you got a P out here. I want you to label that P over there. All right. So what I want now is you're going to draw a segment from P to A to P, and right there. And I want to measure it. I got this little handy ruler here. I want you to measure it, right? And in this case, mine is 2 inches. Yours might be 2 inches, might be something different, but mine is 2 inches. And then I want you to double that distance. So draw a segment from P that passes through A that is 2 times that distance. So if my distance from here to here, right, if my distance from here to here was 2, then your distance is going to go beyond that, right? My distance, it would go beyond that, and now that would be another 2, so that would be a total of 4, and it should look something like that. I want you to label this value A prime. Okay? The next thing you would do is you would do the same type of thing, but we're gonna extend P to B. We're going to measure that length, and then we're going to double that, and then it's going to come out to here. Okay, so I want you to measure it, double it, and then extend that out. And when you do that, I want you to call that B prime. And then we're going to do the exact same thing to C. We're going to start from P to C. We're going to double that, right? And then we're going to make that point. We're going to call that C prime. I want you to use your ruler every single time. Okay, so after you do this, you have A prime, C, B prime, and C prime. I want you to actually connect those values and then draw a little triangle, right? So if I would draw this little triangle that goes from here to here to here, that's what I want to see. Okay, and in doing that, what we have is we've connected points A, B, and C. We have a new image, right? A, B, C prime. And, you know, because this was 2 and this distance here is 4, we've actually enlarged this, haven't we? And so these are 2 similar triangles. They're similar because they're not the same. They're very like each other. What happens with the 2 triangles being similar is that their angle values are actually exactly the same. The only thing that's different is the lengths of the sides. So this little angle here would be the same as that. This angle, same as that angle. And this angle here, same as this angle up here. The difference is the lengths of the sides. So for example, because we actually doubled that, right? Let's say we started off with the length of a side maybe is 3 inches or whatever it is. When I doubled something, now it's going to be 6. And if I said, hey, this is 5, this then would be double that, so 10. And so we have this, in this case, which is called a scale factor, we have that value. So we have dilated this, made it larger by a scale factor of 2. So let's call that an expansion or an enlargement. Okay. Whereas, how does the scale factor influence a dilation? If you notice here that I added another triangle, and I'm calling that A prime prime, and what's gone from A, B, C is now shrunk down to little a, or, you know, A prime prime, B prime prime, C prime prime, and what that is right there is what we call a contraction or a reduction, because we've reduced that value by a half. So like for this one, from here to here, right, I doubled that. But going backwards, I reduced it by a half. And so that's called a contraction or a reduction. Okay, so we have 2 similar figures in dilation from a point that result from some sort of similar figure. Now, how are dilated figures related to their original figures? What do similar figures have in common? So looking at these 2, right, what they have in common is basically a scale factor that we've reduced it or enlarged it depending on, you know, what you're talking about. And that's what they have. I can make a ratio of these 2 values. These 2 shapes are similar if they have exactly the same shape, but are not necessarily the same size. So similar polygons have congruent angles, of course, but their sides are not congruent. The corresponding sides are proportional, which is where we get our scale factor. Now, if I, like on the previous screen, when we were talking about triangle ABC, and we said, hey, that's going to be, you know, similar. This is the little button. This is a little like symbol that I use for something is similar, that little enye kind of thing. And you would say that that's similar to triangle A prime, B prime, C prime, like that. So for this, again, what do you notice? What I would expect that you would notice is this. I'm looking for things that are similar, like this angle is equal to this angle. You would notice that. This angle here, down here where the pumpkin face is, those are equal. If you were to split this triangle up, right, you would have this triangle here, and then you would have the larger triangle, of course, right? And in doing that, I would know this angle is congruent to this angle. Congruent meaning same size and same shape. This angle here, also congruent. And remember, parallel lines, these angles right here would actually be corresponding, right? And then this angle, of course, would be the same because it's actually the same value in both of the triangles. It's the tip of both. And so then the other thing that you can notice is possibly that it could have sides that, let's say that side's 5 and this side is 6, 7. Let's say it's 7. In order to do that, right, I would say 5 is to, let's make that a little bit different. Let's make that 3, right? Like that. Because I would say 5, the little side is 5, and let's say this bottom part is 3, but that means that the whole length, right, would be 8. So I could say 5 is to 8. And what that does right now is that just gave me my scale factor, meaning I can find any other side just based on what I have there as my scale factor. So anytime we do a dilation on graph paper, the center of dilation is going to be the origin, which is right here. All right, it's not always the center, but in this case, it is the center. I want you to dilate this triangle ABC by a scale factor of 1/3. So what I want you to do is think about that too, because if I'm dilating it by a scale of 1/3, am I shrinking it or am I enlarging it, right? So in this case, because it's a factor of a fraction of the original amount, that's going to be shrunk. And so we're going to take this 1/3, and it's pretty simple to do. You basically take 1/3 of each value. So for our A prime, 0 times 1/3 is still 0. But 3 times 1/3 is 1. So 0, 1. For B prime, we're going to take 6, and we're going to multiply that by 1/3, and I get 2. 0 times 1/3 is 0. For the C prime, I'm going to go 6 times 1/3, which is 2. And I'm going to go -6 times 1/3, which is now -2. So my new points are going to be 0, 1 here, 2, 0 here, and 2, -2 here. So this is C prime, B prime, and A prime. And so we draw our new triangle, right, like this. Okay, so we draw our new triangle, and therefore this is a reduction by 1/3, a scale factor of 1/3. Yeah. For this one, I want you to dilate triangle ABC about the origin with a scale factor of 2. So for this problem, instead of dividing by, 1/2 or multiplying by 1/2 or dividing by 2, I'm multiplying, okay, because I want to enlarge it. I'm doubling it. So we have B prime and we have C prime. So take a minute and try to figure out these values yourself, and then check the video for sure. And I'm just going to keep going. We have 0 times 2 is 0. 2 times 2 is 4. 4 times 2 is 8. 0, I'm right here. 0 times 2 is 0. For C prime, I've got 4 times 2 is 8. And again, 4 times 2 is 8. So my new points for A is going to be 0, 4. So here's A prime. We have 8, 0. So there's B prime. And then I have 8, 8. And so this is C prime. And then I'm going to draw my new triangle like that. And so this right here is my enlargement. And this is my scale factor of 2. I doubled it. And I can triple it. I can quadruple it. You can do a lot of different things here. You're just making it larger. For this one here, I want to dilate this about the origin by a scale factor of -1/2. So yes, I am going to be cutting it in half, but at the same time, see that negative? That's also going to have an effect on my image. So I'm going to show you what that does. And remember, what does that do, right? So let's talk about that. So we have A prime, and 0 times -1/2 is 0. And then we have 2 times -1/2, and that's going to be -1. For B prime, 4 times -1/2 is -2, and 0 times -1/2 is still 0. For C prime, we're going to get 4 times -1/2. I'm going to do that twice because that's 4, 4, right? So 4 times -1/2 is -2, and then also again -2. So in doing this, we get 0, -1. We get -2, 0. We get -2, -2. So that, let's see, 0, -1 was here. That's A prime. B prime is here. And then C prime is here. So look what just happened, okay? What just happened was this A that was here is now down below. This B that was over here is now over here, okay? So it did actually rotate this as well as... it rotated it as well as reduced it. It was a reduction and a reflection as well, or a rotation as well. So just reviewing, when you're talking about a ratio of similarity, we've talked about scale factors a couple of different times, But a ratio actually can be rewritten 3 different ways. You can write it as A dot dot B, which is not many people do that. Most people write it as A to B like that, or they say, hey, A to B. But this one right here, for the sake of what we're doing, this is what we're doing here. So if I have my original right triangle here with 6 as my hypotenuse, and this value over here is 10, what I want to know is what's my ratio of similarity. So my ratio of similarity would be 6 to 10. However, for this value, what I would do is I would say, well, if this is 6 to 10, I'm going to reduce that and say, well, that's also equal to 3 to 5, right? So I could actually find the other lengths of my triangle just based on this value here, this 3 to 5, by multiplying or dividing. So let me talk about this again. In your homework, in your packet, you guys have this these C's. When looking at Casey's work, so Casey starts with a C. She created a little a C. And what she did was she went, okay, so I'm going to dilate this by 3. So, and I know it's by 3 because it started off as 8 and now the same side, right? You do have to correspond them, meaning the same side. Remember when we were transforming the shapes, we're not flipping them, we're not doing anything like that. We're just keeping the same size, the same way that they are faced. And so for this, we're going from 8 to 24. So 8 is to 24, right? And so that right there is a scale factor of 1/3. So this is either, if you start here, right, and you go backwards, you're reducing it by, it's a reduction of 1/3. But if you put yourself on this little C here and you go up, it's a dilation times 3. So I want to know if this dilation, did she do this right? Yes or no? You know, how do I know that she did this right? Well, the way we do that is we make a proportion. And we go this side, the same lengths, right? The same vertical, vertical. So we go 8 is to 24 as base is to base. So we go 6 is to 18. And the way you would do that is you would do a couple of different options. You could cross multiply and go 8 times 18. Does that equal 24 times 6, right? And so what is that? 8 times 18, okay, checking on my calculator, is 144. And then 24 times 6, also 144. So yeah, these here this is a similar shape, and they are proportional because the left side does equal this right side. Option B would be, look, I can just reduce these and see that 1/3 is equal to 1/3. You're going to do a little breakout room, and I want to talk to you about just some norms with breakout rooms. Number one, videos are on. Sound is on for everybody. You go into your breakout room, you turn your sound on, you turn your video on. You share and solve together. You're not isolated. You don't do your work by yourself. You talk things out, because the strategies are more important to discuss how you actually arrived at the process than getting the actual answer. Because if you can explain what you did to get the answer, you're way better off than just saying, here it is. That's my answer. You know, there's different things you can do. You can divide and conquer, of course, but I really want you to try to work on working together. There's a birthday order, meaning like you could say, hey, whose birthday was first? You talk first, you talk second, like that. So in your breakout room, what I want you to do is to try to figure out what the other value for X would be, and be ready to share what you came up with in the class. So I would let you go out to the breakout room and then come back. So based on that, let's say if you did that, turn off the video, try to do this yourself, come back. This is what you would do. Most likely you would go, well, 8 is to 20. So 8 is to 20. See this? Left side is to left side. As 6 is to X. Base is to base. And so we would go cross multiply. I would get 8X is equal to 20 times 6. I would reduce that, and I would get X is equal to 20 times 6 over 8, right? I have to get rid of this 8 here. Divide. And then I would just simplify. 8 is actually 2 times 4, right? 4 divides into 20 5 times. 2 divides into 6 3 times. 5 times 3, 15. So that means that x is equal to 15. Now, keep in mind, there's a couple of things I could have done differently. Number one, I'm going to erase this. Number one, what I could have done differently is I could have reduced this right away. And instead of saying 8 is to 20, I could have divided by 2, right? Divide by 2, divided by 2, and said, well, 4 is to 10. Well, actually, I could have divided by 4, right? So let's do that instead. Instead of dividing by 2, I'm going to divide by 4. So divide by 4, divide by 4, right? And I get 2 over 5 equals 6 over x. Cross multiply, I get 2x equals 30, x equals 15 again. The other option that I could have done right in the very beginning up here was this. Instead of saying 8 is to 20, I could have said 8 is to 6. Left side is to my base as left side is to my base. So 8 is to 6 as 20 is to x. I would still reduce a fraction if I could. 8 is to 6, I would divide that by 2, and I would get 4 is to 3 as, in this case, what is that? 4 is to 3 as 20 is to x. I get 4x is equal to 60, x equals 15, x equals 15 again. But technically, when you're talking about a scale factor, you're not comparing the same sides of a shape. I'm not going to go 8 is to 6, okay? I want to compare the left side to the left side. I'm comparing the same sides. And actually, it doesn't matter which sides you compare as long as they're not the same shape. So I know that's 6. This is 15 now. 6 is to 15. If I divide that by 3, I get 2 is to 5, which is the same scale factor if I said 8 is to 20. Because my scale factors have to be the same regardless of, which ones I'm doing. All right, so you do have an exit ticket. You're going to use graph paper to write the question and your solution, and you are going to submit that to Canvas. But first, we're going to send you off in your breakout room so you can discuss that other question, and then come back to do the exit ticket. So we've got the homework, which is 3.1.1 and 3.1.2. And here's your exit ticket. What I would want you to do is, this is a reduction. You have a scale factor of 1/2, and I want to see what this looks like. You're going to submit this to Canvas when you're done. Okay? So that's it. If you have any questions, please see me in office hours, and I hope this helped in some way.